Okay, so in one of the prior videos we have solved a problem of a rolling disk with a slot that has a pin that is connected to a horizontal bar, and the goal of the problem was to find the angular velocity under certain conditions. So let me just quickly first draw the system that we had considered in that problem. So the problem, the system that was considered in that problem is as follows. So there is a disk that is rolling without slipping on a horizontal surface, and on the disk there is a slot, and there is a pin on the slot which is connected to a bar that is constrained to move horizontally. With a velocity V0, and the radius of the disk is R. This is the center C. The pin is at the point P, and this slot is expressed. The slot is at a distance of D from the center. So if you draw a radial line and you call this the E radial unit vector, and perpendicular to that and parallel to the slot is the E theta unit vector, and let's say that at a certain instant, so this, by the way, this ER is perpendicular to the slot, and at a certain instant this ER is making an angle of theta from the vertical, and the distance between the center and the slot is D. So this is the setup of the problem, and we know that the bar is being drawn with a velocity V0, and we want to determine the angular velocity of this disk. So determine the angular velocity of the disk. There is one other parameter that needs to be specified, and that is the distance between this pin and this perpendicular, and that distance is given by the parameter x. Okay, so at an instant that distance is x. Of course, x is variable and theta is variable. The goal here is to find theta dot, and it is given that the bar is moving with a constant velocity V0, and the bar is at a height h, small h, from the ground. All right. So in solving this problem, we will now we will take method 2, and that is going to be direct differentiation. We have stated that the purpose of these videos is to discuss to introduce different techniques in dynamic analysis, and so in keeping with that goal, the purpose of this video is to show an alternate method to solve that same problem, but now using a direct differentiation method. In the previous problem, where we had used the approach of relative velocities, in addition to theta dot, we also found out x dot. So we can repeat, we can put that also as a requirement of this problem. That is, determine x dot. Okay, and once we find out theta dot, determining x dot is not going to be a big deal. So how do we set up this problem for the direct differentiation method? So what we do in the direct differentiation method, so direct differentiation refers to determining velocities from direct differentiation of position vectors. So the approach is really very fundamental. The approach basically is that since velocities are just direct differentiation of position vectors, so if I'm interested to find the velocity of a certain point, all I need to do is write the position vector of that point and then take the derivative as a function of time. And so that is the approach that we are going to explore here, and we are going to demonstrate, and we'll show that the results that we get are the same as the results that we obtained using method 1. In method 1, which is in a prior video, we have used the approach of relative velocities, where you have the relative velocity within a moving frame, the omega cross rho kind of concepts, the three-term velocity of a certain point is equal to the velocity of a different point plus omega cross rho plus rho dot r, and so on and so forth. The three-term velocity expression that we have used for rotating frames. Now, one note over here is that as we solve this method of direct differentiation, we'll still use this ER E theta, and in fact there is a EZ which is pointing into the page perpendicularly downwards. So that triad is still going to be there, and it is a rotating triad. But instead of using the rotating frame equations, we are going to go to the fundamentals of using the position vector and then differentiating it. So we'll go back to the fundamentals and do that. So we make a note that we still use ER E theta EZ as the coordinate triad. All right. So let's look into how we go about the solution. Since the objective of this problem is to use the position vector to find out what the velocity is, so angular velocity and x dot, we will first formulate the position of the point P, because clearly P is a point of interest, and so but since we have to first determine the position of P and then differentiate it, this is where sometimes the direct differentiation method requires you to do some extra work. So in this case, we have to define a fixed reference frame, and let's call that capital X, capital Y. Okay, so we have to define it because our position of the point P has to be with respect to an inertial and a fixed reference frame, so that we get the absolute position, and then when we differentiate it, then we can say that that derivative is the velocity, the total net velocity. So we can say that Rp, that is the position of P, is equal to the position of C, right, Rc, plus if you use this unit vector ER and E theta, then Cp can be expressed as, you can see that it is d times ER plus x times E theta, right? In other words, we can then say that Rp is equal to, now what is Rc? Now if you assume that the point C at a particular instant, arbitrary instant, is at a distance x, then Rp is equal to Rc, which is going to be xi, if I is the unit vector along this capital X, plus capital Rj, where j is the unit vector along this capital Y, plus der plus xe theta, right? Now writing a position vector or a velocity vector in this form using two different sets of unit vectors is not a good idea, because you won't be able to add I and ER, you won't be able to add J and ER, or for that matter E theta, because these are unit vectors in different directions. It's always a good idea to reduce things in terms of unit vectors in a certain the same unit vectors for all the vectors. So we'll do that, but before we do that, let's then take the direct differentiation of this position. So we can then say that Vp is equal to x dot I plus Rj, the derivative of that is going to be 0, plus der dot plus x dot E theta plus x E theta dot. Oh, I made a mistake here. This I'm using a x over here while I have used the same variable x to represent the distance along the slot between the point P and the center of the slot. So I need to change this. I'm going to call this x tilde, okay, just to, so this is going to be x tilde dot, okay. So x tilde represents the instantaneous position of the center of the disk. Now note over here that I didn't take the derivative of I, because I dot is equal to 0, since I, i.e. x, has a fixed direction, right? So this ij is not a moving frame, this is a fixed frame, hence hence I do not need to take a derivative of I, but I do need to take a derivative of ER, and I do need to take a derivative of E theta. So now what is this x tilde dot? This is the rate at which this point, the center C, is moving. Now we have already seen, if you go back to the earlier video on method 1, and it is quite obvious, because this is a disk that is rolling without slipping on a horizontal surface. So I should put that, rolling without slipping. Okay, since this disk is rolling without slipping on the horizontal surface, so what happens is that the velocity of this point C is going to be not only horizontal, but its horizontal velocity is going to be theta dot times capital R. So you have theta dot times capital Ri plus der dot plus x dot e theta plus x e theta dot, right? So now, so that's the second line. Now let us consider this direction I. We need to replace this I and express I in terms of ER and E theta. So let's do that. So here is our I direction, and this is horizontal, and if you superimpose that on that the ER and E theta direction, ER and E theta direction, then this angle is theta, and so this angle is theta, and so therefore the direction I is nothing but cosine theta e theta plus sine theta er. Okay, and we note that Vp is also V naught I. Okay, so essentially then we can write, so therefore V naught cosine theta E theta plus V naught sine theta ER, which forms the left hand side of this equation, is equal to theta dot R cosine theta E theta plus theta dot R sine theta ER plus DER dot plus x dot E theta plus x E theta dot. So that's another level of expansion, simplification, if you want to call it that way. But we are now basically expanding out all the vectors, and the approach that you can see does not use any relative velocity concepts. It is essentially starting from the position vector and then just going about taking the derivative of the position vector. Now all we are left to do in this in further simplifying is to find out E dot R and E dot theta, or E theta dot, ER dot and E theta dot. So let's find those derivatives. These are the derivatives of the unit vectors. So you have the ER, E theta, EZ, and our right-handed coordinate system is such that ER cross E theta gives EZ, and so on. Okay, so therefore let's just quickly take a look which two unit vector derivatives we want, ER dot and E theta dot. So let's derive the expressions for those two. So ER dot is omega cross ER. This is a fundamental equation. As we have discussed earlier, the rate of change of a unit vector is equal to the angular velocity of the unit vector cross the unit vector itself. What is omega here? Omega here is going to be the angular velocity. As you can see, using the right hand rule, if you curl your fingers around in the direction of increasing omega, then the thumb is going to point in the direction of the vector of angular velocity. So theta is then the angular velocity is theta dot EZ cross ER. So Z cross R is E theta, so this is equal to theta dot E theta. And E theta dot is equal to omega cross E theta. which is theta dot Ez cross E theta, which is, so Z cross theta gives negative R, so minus theta dot ER. Okay, so we have theta dot theta dot ER. Right? So we have the two unit vectors, or the two derivatives of unit vectors that we need. So going back to our expression then, the expression is V naught cosine theta E theta plus V naught sine theta ER is equal to theta dot capital R cosine theta E theta plus theta dot capital R sine theta ER plus dER dot, so ER dot is theta dot E theta, so d theta dot E theta plus x dot E theta plus x times negative theta dot R, so x times negative theta dot ER. Right? So then what we do is, as you can see in both sides of the equations, we have E theta and ER. So if we take the E theta terms, then we have V naught cosine theta is equal to theta dot R cosine theta plus d theta dot plus x dot. So this gives us equation 1. So this gives us equation 1, and then ER terms, if we put them together, then we will have V naught sine theta is equal to theta dot R sine theta. So we are putting the minus x theta dot. Right, so that becomes our equation 2. So we have two equations. Now, therefore, from 2, we have theta dot is equal to V naught sine theta divided by R sine theta minus x. So we have the expression for the angular velocity. However, there is one step still to go, and you have seen this step in the previous problem, or rather in the previous method that we used to solve. See, we have our expression for theta dot, but it uses the variable x, and we know that x and theta are connected because the disk is rolling. So as the disk rolls, we know that causes theta to change, and as theta changes, we can see from the structure that the theta has a 1-to-1 relation with what the value of x is going to be. So given a theta, we'll know what x is, and that relation is found by imposing the constraint that this point P is always going to be at the height h. And if you impose that constraint, then what you have is, so I'm going to say, now imposing, okay, so now imposing that bar always stays at height h, we have, so if we impose this constraint, then you can see that the height of the point P, that is the y coordinate of the point P, you can decipher it from here. You see that if you consider the point P, then the height of the point P can be found out by noting that the point C is at a distance r from the ground. Then you go by a distance d in this diagonal direction, and then you go by a distance x along the slot. So the vertical distance that you go from the ground to P is r plus d cosine theta minus x sine theta. Okay, so let me just write that down. Y of P, that is the y coordinate of P, is equal to r plus d cosine theta, and minus x sine theta. Okay, and that is equal to h. So basically x can be given by r plus d cosine theta, okay, minus h divided by sine theta. And you will find this discussion and this derivation in greater detail in the other in the prior video which I made on this disk rolling with a slot rolling on a horizontal plane. The same problem was solved using the relative velocity method. So now using this expression for x, I can substitute that in, let's call this equation 3. So I'll say, therefore, substituting in 3, we have theta dot is equal to V naught sine theta divided by r sine theta minus r plus d cosine theta minus h divided by sine theta, which is v naught sine squared theta divided by r sine squared theta minus r minus d cosine theta plus h, and that is the expression for theta dot. And once you have this expression for theta dot, you can go back to equation 1 and solve for x dot. So that is the alternate approach, and if you check with the previous method, the video on the previous method, you will be able to verify that indeed we have the same answer as obtained using method 1 where we used relative velocity. So I'm just going to put a note that check that we get the same answer for theta dot using method 1, relative velocities in rotating frame. Okay, so again, in following our goal of exploring different techniques in solving dynamics problems, this problem was formulated, proposed, and solved to show an alternate method of solving this problem, which was already done using a prior was shown with the prior method. Here we have shown a different method, and that is of direct differentiation. One thing that we observed with this direct differentiation approach, or the salient feature of the direct differentiation approach, is that we need to provide the absolute position of the point whose velocity we are about to express. And often in a problem on dynamics, that may require us to define a fixed coordinate frame with a fixed origin, so that with respect to that point we can find the position of the point of interest. So that sometimes can create a little bit of a problem, because depending on the problem definition, it may not be easy to indicate the position of that point with respect to an arbitrarily located fixed reference frame. And when that happens, when the problem becomes complicated, that's where we try to directly use the relative velocity approach. Here the idea of direct differentiation was not that complicated, because we could easily define this fixed reference frame, show the position of the point P, and then go from there by taking the direct differentiation. So that's it for this video. Thanks for watching, and then we will keep posting more videos as we move forward with further and further discussions on these techniques of solving problems in dynamics. Thank you so much.